All right, hey guys, Mr. Kyle, Myers Mathematics, and let's just jump right into it. This is that one thing in math that I don't know if anyone really pronounces it correctly, so I had to scour the internet and find a actual French person to pronounce this correctly, and I still can't pronounce it because I'm an English person. So it's some people call it DeMoivre's or DeMoivre's, but it's if I can try to pronounce it correctly here, it's DeMoivre's theorem. So that's what we're going to do. But in order to see what it is and how it works, I like to just do an example. I don't like to get into really technical stuff. We're going to start with if I want the cubed roots of 8. So what if I want the cubed roots of 8? Right? So one way to look at this is if I say x cubed minus 8 equals 0, or if I were to say, okay, so what is x going to be equal to when x cubed minus 8 is equal to 0? So the simplest way to do this would be to just say, okay, so I take the cube root and blah, 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 and x is equal to 2. And that is one of the cubed roots of 8. But see, with this person, DeMoivre's, their theorem basically says that whatever root you do of a number, there's that many answers. So if you take a cubed root of a number, there's 3 answers. We're actually missing 2 of them. If you were to take a 5th root, there'd be 5 answers, and 6th root, 6 answers, so on and so on. We have one of them, and the only answer that's a real answer. But they said that there's 3. There's 3. And so besides real numbers, there's imaginary numbers. And then besides real and imaginary numbers, there's numbers that are just complex numbers that are neither real nor imaginary. And the other 2 answers are not real answers, but they are complex answers. So another way to get this without having to even use DeMoivre's theorem is if we use the difference of cubes factoring method, which is I take the cubed root of x cubed and the cubed root of 8. And then what I do from here on out to complete the the difference of cubes factoring method is I times the first by itself. I take the opposite of the first times the second. So x times -2 would be -2x. And then I could take the opposite of that and get plus 2x, right? That's the most trickiest part. But the middle term is the opposite of the 2 multiplied. Lastly, it's going to be the last times by itself. So altogether, that was the first times itself, the first times the other, and then the other times itself. And there we go. So then this would be equal to 0. And then I could say, okay, well then x would be equal to 2, which we already got that from earlier, so we already reestablished that. But then also x squared plus 2x plus 4 is equal to 0. So that's also a thing. Now, then I'm going to have to try to factor this, but there are no factors of 4 that add to 2, not in the natural numbers or even the rational numbers. So what I want to do then is use quadratic formula. There we go. It escaped me for a second. I want to use the quadratic formula. A is 1, B is 2, C is 4. That's just a little bit down too far. There we go. Pull that up a little bit. And then what I'm going to do is I'm going to try to keep all of this example in blue and on the left-hand side as much as I can here. So I'm going to create a little pocket here. And we're going to do the quadratic formula, which is x is equal to -b. And I like to do the plus or minus the square root stuff off to the side. So I'm going to do that kind of on the side here. And so that's going to be square root of b squared, so 2 squared, minus 4 times a times c. So that's going to be 4 times 1 times 4 is 16. 4 minus 16 is the opposite of 16 minus 4. 16 minus 4 is 12, so that's going to be -12. -12 is, let's see, what do I want to put first? I want to put the 4, and a -1, and a 3. So I'm going to break it up like this specifically because 4 is a square number. -1 is the part that if I take the square root of it, it just becomes the symbol I, and then the root 3. Some people like to put the I on the other side of the radical. I actually usually like to do it that way, but it's really easy to forget that it isn't under the radical anymore and then put the I under the radical, and then that would be incorrect. So we want to avoid doing that. So this is probably one of the safer ways to write it, 2I root 3. You could write it as 2 root 3I. You can technically write it in any order you want because you're timesing them all, but you know, it's up to you. So 2I root 3, that is b squared minus 4ac. So x is equal to negative b plus or minus the square root of b squared minus 4ac, which is 2I root 3. 2I root 3, you gotta squeeze that in there, all over 2 times a, which is just 2. And then it will simplify because everything divides by 2, so then that's negative 2 over 2 is negative 1, plus or minus, and then 2 over 2 cancels again there, and I get I root 3 or root 3I. I actually like to write it with the I at the end. Just make sure you don't put that sign over the I as well if you're going to do it the other way. So there's our other 2 cubed roots of 8. Now I haven't actually done DeMoivre's theorem yet, but I have all of the answers because sometimes there's a loophole. Sometimes you can get all of the roots of a number without having to do DeMoivre's theorem. But sometimes, especially for higher roots, there's not really a nice alternative method to find out what the roots actually are. So now we're going to do DeMoivre's theorem. And that involves a really kind of a complicated formula. I'm going to see if I can write this right underneath my face because I can't actually see my face. You guys can see my face, but I can only see my face if I look over on my other screen here. So this formula goes kind of like this. It's so our cubed roots are going to be, so if we want the cubed roots of a number, so let's say, you know, all of the cubed roots of z, then that's going to be equal to the cubed root of r, and then that's going to be multiplied by the cosine of theta plus I times the sine of theta. All right, and this is just getting a lot more complicated at this point. Let me move this down a little bit so you guys can see that. And I might move it back up a little bit as we go because I might need the space. So this is the more complicated formula. This is when we're talking about complex in polar. So this topic, if you haven't already clicked on it because you're in pre-calc, this is a pre-calc topic. So if you're not in pre-calc yet, this is going to really blow your mind. And if you're in pre-calc, it probably will still blow your mind, even if you're learning this currently. But if we want to find out what r and theta are, we need some formulas. We need theta is equal to the tangent inverse of y over x. And in this case, y is the imaginary part of the root that we're trying to find, and x is the real part of the root that we're trying to find. Okay, and then we also need r, and r is going to be equal to the square root of x squared plus y squared. So this formula will find the roots of anything, because it's set up to where you can find any root of any number. That's how powerful, I guess, this formula is that it can find the root, all the complex roots of any complex number. So a real number is only a small, tiny subset of all the complex numbers, and same thing with imaginary. Imaginary numbers are only a small subset of all the complex numbers. So out of all the complex numbers that are out there, you can find any root of any of those complex numbers, and you can find all the complex solutions. Whew. Okay, now we're just trying to find the cube root of 8. If you were to write 8 as as a complex number, it would be 8 plus 0i, aka a plus bi. A is 8. In this case, we're actually using x. So x would be 8, and y is 0. So it's actually kind of useless to use this whole formula here, because then I'm plugging in 0 squared, and then I'm plugging in 8 squared is 64, and then the square root of 64 is 8. So our r actually ends up being 8. Now for our tangent, though, it would be y over x, so it's actually tangent of 0 over 8, and it's the tangent inverse specifically, so tangent inverse of 0 over 8, which is the tangent inverse of 0, which is 0 unless I need to be in the other quadrant where I get a tangent value of 0, which would be 180 degrees. So it's either going to be theta is 0 degrees or theta is 180, and in this case it's going to be 0 because if I were to graph this complex number as a point, it would be the point 8, 0. So theta is, oh, not 8, sorry. Theta is 0 degrees. Okay. So then from here, we start plugging in our stuff. And specifically this theta here, actually the more complicated version of this formula is, sorry, I did not write this formula correctly the first time. I would go back and redo the video, but I don't know, other than that little hiccup, it's not too bad. So hopefully you don't have to, hopefully you didn't write this formula down in pen. That's going to be theta, and that's 360k, and then theta plus 360k, I'm having to squeeze this in here, sorry, over n. Phew, okay. And n, by the way, is the root itself. So if I wanted to really generalize this formula here, then n would go here, and it looks like my pen is, either the pen is laggy or the whiteboard is laggy. So I'm going to give it a second to cook here. Let's see. Ah, there it goes. Okay, so the nth root. The nth root. And n is going to be 3 in this case. So actually, let me write these next ones on the other line, because I had to kind of squeeze that one in there. So n is 3 because we're trying to find the cubed root. Theta is 0 degrees because the point 8, 0 would be on the positive x-axis at 0 degrees above or below from the x-axis. Okie dokie. And then k is just anything you want it to be. Now, k, typically what you want to do with k is you want to start at 0, and then you want to count to however many n's there are. So if there's n is 3, then I want 3 k values. So k is equal to 1 and 0 and 2. So 0, 1, and 2. There's 3 different k values. That'll cover all of the unique cubed roots of 8. Okay, I know this is like overkill, but the reason why I want to do it this way after doing it the easier way is because normally you do the hard way first, and they're like, oh, but wouldn't it be nice if there was an easier way? And then you do the easier way, and then everybody's like, oh, thank goodness. Well, no, I'm doing it in the reverse way. But that's to show you that it works, and to show you that sometimes you can get around using DeMoivre's theorem, but sometimes you can't. So if you can get around it, you want to, but if you can't, then you just gotta do what you gotta do. So we're gonna go ahead and plug this stuff in. So it's gonna be the cubed root of r. So n is 3. R is 8. I'm taking the cubed root of r, so that's just 2. All right, and then that's going to be the cosine of, now I'm going to plug in, my theta is 0, so 0, n is 3, so it's 0 plus 360k over 3. I'm going to plug in 0 for k as well, so that's going to be 0 plus 0 over 3, which is just 0. Cosine 0 plus I sine of 0. So notice that the value that I put for the cosine and the sine are actually going to be the same thing. It's theta plus 360k over n for both the cosine and the sine. And then I can, actually I don't need to approximate this, it's going to be an exact number. The sine of 0 is 0, so that's all going to just cancel. Cosine of 0 is 1 times 2 is 2. So this is just 2. Okay, so then next it's going to be when k is 1. So I'm going to do all the same values. The only thing that's going to change is k. I'm going to make k equals 1 in the next time. So it's going to be the cubed root of 8 again, so that's 2. Then I want the cosine of, now theta is always 0. Theta is 0, where did I put that right here? Theta is 0. And then it's 360 times 1. So now it's 360 over n is equal to, where is it? 3. So that's going to be 360 over 3. 360 over 3. Here's one thing I like to do is just leave that alone for right now. I already simplified it quite a bit in my head. But then one thing you can do is you can simplify it a little bit right here, and then simplify it further over here since they're the same thing. So 360 over 3, that's going to be 3 over 3 is 1, 6 over 3 is 2, so that's 120 degrees. See how I did that? So it's a little trick you can do without having to write an extra step for simplifying them, is you can simplify it a little bit. You could even simplify it a little less than I did to get 360 over 3. But just to show you how it works here, you can simplify it a little bit and then simplify it a little bit more to get this. And then just remember that this number is the same as that number. Okay, so this one's going to be a little bit more complicated. The sine of 120 degrees. So let's see, 120 degrees, that's going to be in the second quadrant. That's going to be 60 degrees away from 180, so that's a reference angle of 60. Sine of 60 is the square root of 3 over 2. It is in a positive quadrant for sine, so that would end up being, lost my train of thought. Oh, root 3 over 2. There we go. Root 3 over 2. So then that's going to be the cosine of 120 as well. 120, still in the second quadrant, 60 degrees away from 180, so it's a 60-degree reference angle. The cosine of 60 is a half, but it's in a negative quadrant for cosine, so that's going to be a negative 1/2. Okay, then I want to times by 2. So that's going to be 2 times negative 1/2 is negative 1. And then that's going to be 2 times root 3 over 2. So the 2's cancel there as well, and it's going to be root 3i. So plus root 3i. So I've got 2 out of my 3 answers so far. I'm going to have to move this just a little bit to be able to fit that last one in there. Here we go. So the last one's going to be 2, and then cosine. And then remember that theta is 0, so it's just 360 times 2. So that's going to be 360 times 2 over 3. This time I'm simplifying it a little less. You can see how this simplifying as you go thing really helps here. You can actually divide 360 by 3 first, because that would actually be easier. 360 divided by 3 we've already done. We already know that's 120, so just be double that, which is 240. 240. All right. Then sine of 240 and cosine of 240. All right, I'm going to move this down just a little bit more. So let's start over here. So cosine of 240 degrees is going to be in quadrant 3, and that's going to be 60 degrees away from 180. So that's a 60-degree reference angle again. And so that's going to be cosine of 60 is a half. We're still in a negative quadrant for cosine, so that's going to be negative a half, negative 1/2. And then for sine of 240, same thing. It's in the third quadrant, 60-degree reference angle. Sine of 60 is root 3 over 2. However, we're now in a negative quadrant for sine, so that's negative root 3 over 2. And then the same thing happens when I distribute the 2. The two denominators cancel. So I get negative 1 again, but the sign changed for this one, so now it's minus root 3i. And there we go. Notice how the answers ended up being the same. So this and this and this. There's all 3. Now, if I were to keep going, let's say I plugged in a k equals 3, which I'm not going to, but if I did, and you can try this, you can pause the video if you want and see what happens. You're actually going to get, I believe you would start by getting 2 again. If I remember right, you should get 2 again, and then the next one would be the negative 1 plus root 3i, and then the next one would be, and it would just cycle infinitely like that for all values of k. So there's only going to be 3 unique values of k. You can test me if you want and see, but I'm pretty sure that's what it does. It just kind of cycles through. But there you go. So we get all 3 roots of 8, and there are only 3. That's another thing about DeMoivre's theorem, is that whatever the root is that you're taking of the number, that's how many complex answers there are. No more, no less. It's not like the possible number, like you sometimes say with real numbers. Like there's possibly a real number of answers when I have a cubed power of x and I'm solving for it or whatever. There's possibly 3 real answers, but there's always 3 complex answers. So there we go with DeMoivre's theorem, and that is, I looked it up. That maybe I'll put the video link where I found that. It's I don't know, just some random guy I found on YouTube, Julian Mikel. I guess is he's an actual Frenchman, and he just has a YouTube video on how to pronounce things in French. So maybe I'll put that down below, and you can check that out. Also down below, I have my website links. You can go to my website and check out all my free resources on there. You can also sign up for tutoring if you're looking for a tutor. I think on the main page, it should be the 5 math mistakes everyone makes and how to avoid them. So you can go check that out on my website, Myers Mathematics. And I think I also have my email down below as well if you want to reach out to me if you have any questions. You can also just put it in the comments down below, and I'll check that out as well. So without further ado, I hope that's been helpful, and I'll catch you guys in the next video real soon. Blessings, y'all.